Okay, so thanks for sticking around for the last talk of the day. My name is Dino Viehland. I work at Microsoft, and I've actually been working on Python stuff at Microsoft since 2005, as crazy as that kind of seems. So today I'm going to talk about building a JIT for Python, and this is a JIT for CPython, actually. So this is, I think the reason for this might be kind of obvious to a lot of people, but it's really to improve performance of CPython. And what really inspired me to do this was there's a talk at PyCon this year at the Language Summit where Larry Hastings was asking what can we do to improve adoption of Python 3. And I think one way to do that is to improve performance, and kind of an obvious way to improve performance is to add a JIT to Python. JITs have been used in a lot of places to improve performance. I think everyone knows and has seen what's happened with JavaScript over the past several years as the different browser implementations have gotten extremely competitive with each other and have been working on better and higher performance JITs for their JavaScript implementations. That even has translated over to the server side where you have things like Node.js, which has adopted JavaScript as its programming model. We even see languages like Java, which we don't think of as dynamic languages, benefiting from JITs in a lot of ways, where they can take what is more static code, but still somewhat dynamic via virtual function calls, and greatly enhance the performance of their own code by JITting it at runtime instead of compiling it ahead of time. And I also just kind of think compilers are fun. Before, I've worked on Python tools for Visual Studio at Microsoft. I worked on IronPython, which was a Python implementation, which was JITted using the CLR. And before that, I actually worked on the CLR itself, and so I really kind of like these low-level things. And so I've been working on Python tools for Visual Studio and some service stuff recently, and this was a fun way for me to get back to those sort of roots. So, my plan was fairly simple. Python has a bytecode-based interpreter, and .NET actually has a bytecode-based interpreter. Python's bytecode is much higher level than .NET's. It has things like opcodes for addition, which are very high level and operate on all sorts of objects, whereas .NET's has addition, but it's really adding two numbers. And the other interesting thing is Microsoft just recently open sourced the CLR, the entire stack, including a relatively new JIT called JIT. So I was thinking, well, they're both stack-based. This should be pretty easy. I can just translate between them. I just have to go through and do the work, and it should be pretty straightforward. And along the way, hopefully I can also come up with a standardized JIT interface for CPython so that other people can plug in JITs as well. So it's not just this one JIT, and maybe we can get some of that competitive spirit that we see going on in the JavaScript and browser space. So I picked Core CLR for several reasons. The first is it really is a JIT. It's designed to compile methods quickly with little overhead. And that's in contrast with the JIT that the CLR used to have for its 64-bit JIT, which was actually based upon a full compiler. And that was slow. I saw that when I worked on IronPython. Our x86 performance, when it came to startup, was still kind of terrible compared to CPython, but when you looked at x64, it was a travesty. So the fact that the CLR threw this out and started with a new JIT that was designed to be a real JIT was promising. And you see a lot of other attempts to do JITs for Python and for other things, and a lot of them will use LLVM. LLVM's there. It's a nice common compiler infrastructure, but it's a real compiler, and it suffered from the same problems, or suffers from the same problems that the CLR JIT really suffers from before they rewrote it. The other nice thing about the CLR JIT is it has support for both object-oriented APIs where you can do things like virtual function calls, but it also has support for low-level primitives. So one of the goals early on with the CLR was the ability to compile C++ code down. And you could just take any random program. I think they demoed Quake being recompiled into IL, and it all just worked. and the JIT can compile it. And so my implementation is actually not using any of these object-oriented opcodes at all. It uses call to call methods, but other than that, it's generating a bunch of pointer arithmetic style code. So the other thing about core CLR is I knew that we could get good performance from the JIT. And that was from my work with IronPython, where we actually had some really nice numbers coming out of it. It was not good on startup cost, and that was something that we tried to fight over and over and over again. But the nice thing about CPython is we can keep the eval loop, which starts up extremely quickly, and then JIT methods as they become hot. And I obviously know IL, I know the CLR, I worked on the CLR team before I started doing Python stuff, and I just thought it was kind of cool that we open sourced the CLR, and I could use it. And then I keep mentioning the open sourcing of the CLR, and the key thing here is I'm not actually taking the CLR that's sitting on your machine and using that to compile code. I actually rebuild the CLR. The JIT is actually its own DLL if you have a Windows machine and have the CLR on it. But you can compile it into its own lib. It's standalone. I statically link that into my pyjit.dll, and it's just a small DLL, which is a standalone JIT at that point. The CLR team's working on porting the JIT over to Mac OS X and Linux, and so this will actually all be cross-platform at some point as well. And of course, you're thinking, well, JITting Python, that's been done before, right? And it has been done, but I think people always kind of go off in weird directions. I'm trying to go off in a slightly different direction. So of course, there's Numba, which is LLVM based, and I mentioned kind of how full compilers are a little bit slow to start up. It's also focused more on numeric code, and so I want to focus on just the ability to compile any old Python code. But it is the most active JIT implementation for CPython right now. There's Unladen Swallow, which also focused on LLVM, and in fact, they were kind of one of the first consumers of LLVM as a JIT, and they had to fix tons and tons of bugs in LLVM to make it a successful JIT. And Google ended up walking away from that project after they weren't quite able to get the performance gains they wanted. There's Psycho, which is no longer under active development, but it was the first Python JIT. It did its own custom code generation, which I think in some ways is a little bit scary. It's kind of a maintenance nightmare. It's going to be difficult to port things to new platforms because you have to go and rewrite your code generator again. And I just kind of don't really want to go down that route. And ultimately that was replaced by PyPy, which is scary in its own way, but still extremely successful. So PyPy, obviously the fastest Python implementation that's out there. They suffer a little bit from startup time, but it's nothing like a lot of the other LLVM-based implementations. And they also have their own custom JIT that they have to maintain. And it's a different Python implementation. So you kind of give up everything that you know and love. Like your C extensions might work, but you definitely have to rebuild them. And that can be said for IronPython and Jython and Piston, which is another new implementation. There's advantages to going to new implementations. IronPython and Jython kind of give you the best of their underlying VMs and all those libraries. But sticking to CPython has a bunch of advantages, and just you get absolute compatibility and you get everything that is actually out there. So one of my goals here was to come up with a JIT interface. And right now that is extremely simple. There's a function to initialize the JIT, which currently is invoked at startup time, but that's probably a bad idea. And that might go away, who knows. There's a function to eval a piece of code that has been compiled. And so when you compile a piece of code, you get a PyCode object and return this function pointer that CPython can call in place of doing its normal eval. This takes a frame object, and that might seem a little bit weird in that really to get good performance out of a JIT, you want to get rid of the frame objects entirely. But there needs to be something that comes in for that first invocation. And from then on out, the JIT can actually start doing calls between functions, getting rid of frame objects and not creating them, inlining functions, and all of those good things. So I think this is a good common starting point. And then I have JIT free here. You know, we've got to clean up at some point, but I don't actually do anything with that yet. So that's kind of to do. There's probably some more things that will need to be defined for a JIT interface. We might want to have some sort of annotation system. So you see this in Numba where you can say this actually takes these specific types. There's ints or bools or strings or whatever, and the JIT can generate more optimal code. But I really kind of hope that won't become necessary. Something that Unlead and Swallow looked at doing, which is actually really useful, is having callbacks for when dictionaries change so that you can invalidate code. So that rather than assuming that range, you have to check to see if you're calling range, and if you are, then you're actually going to get an iterator of numbers. You can just discard that code and not do any checks inline. So those are useful for both the built-ins dictionary as well as the globals dictionaries. A function to call to continue evaluation of a frame. So sometimes you may be running optimal code and your assumptions aren't true anymore. And it would be nice not to have to generate fallback code so that you get more dense code that has better abilities to fit inside of caches. And being able to just fall back to the Python JIT and say, hey, evaluate my stuff here. I was last at this opcode. Thanks. And then finally, something that we saw in IronPython was that sometimes you'll have code that spends all of its time in a function and it's just looping inside of that top level function, and you really want to compile that loop. I'm not quite sure what this looks like in order to avoid not adding significant overhead into CPython normally, but that would be something that's pretty useful as well. Okay, so what does this end up looking like? Here's a simple function. It adds two numbers and returns them. And Python, the bytecode is extremely simple. So it loads A, it loads B, it calls the binary add opcode, and it returns the value. So we translate that into .NET bytecode, and it gets a little big. So that's what that ends up looking like. I'll just let you read and soak that in. Got it? Okay, cool. So I'm not going to go through this opcode by opcode or anything insane like that because, well, I don't want you to all run out. So instead, let's look at kind of what's going on to actually generate this code. And so this is the source code from the JIT itself. And kind of the first thing that we ended up generating is actually a method prologue. And one of the things that I've tried to do is just make JITted code work exactly like unJITted code. So this first bit, if you've ever looked at a Python frame object, it has the last opcode that was executed in it. And so we pull the address of that variable out of the frame object and store it as a local so that we can update it whenever we need to. And then the first thing that the pyeval function in CPython does is it pushes a frame, and so we go off and do that. The next thing that we're going to do is load those two variables, right? And this is actually represents a good chunk of the code that you saw on that screen. A lot of it is kind of unnecessary. We know that those parameters will never not be assigned, but right now I've done no real optimization on the JIT whatsoever. And so this is pulling out the local from the frame object, and one interesting thing is that our locals are still in frame objects. So if we went off and called into something that called sys.getFrame down the stack, they could go up and they could find the locals and pull them out right now. And that's a potential place of optimization in the future. But then we go off and we actually check to see if the local is set or not. If it was null, the local is not defined, and we're going to have to raise an exception. It'd be very easy to go through and know if a local was never deleted, that it's always going to be assigned. It's a little bit more difficult for non-locals, because you have to understand the flow control of the function, or for non-parameters. So that's a simple optimization that can be done, which will reduce the code in the future. Finally, we dupe the value on the .NET stack, and we call incref on it, which consumes one of the values, and the variable that we loaded was left. Next, we do add. Hey, that's easy. It's a method call. So all of the operators are basically this easy. We have two values on the stack, and we can just call into a helper method, which calls into a method in CPython, which does the addition. Now, addition can fail. It can raise an exception, in which case it will return null. And so we have check error, which we call, which is actually going to do the null check and raise the exception. And this is what check error looks like. So it's going to compare, see if the value is null. If it is, then it's going to branch around. Otherwise, it's going to branch to a label where we actually raise the exception at. There's this to-do here right now. So if B was not defined after A plus B, we would have pushed A onto the stack. And we have to decref A, and that doesn't happen right now. So that's still kind of an outstanding thing to do, although it's just a little bit of work. So, it leaks a little bit of memory occasionally when you're throwing exceptions. And I mentioned last I before, updating that. We don't have to update last I all of the time. There's instructions that can't possibly fail, and the user's never going to see last I in that case. And so if it's something like dupe, we aren't going to actually update that again and again and again for no useful purpose. So sometimes we update these and burn them in. Hopefully, we can get smarter about this and get rid of this too at some point. But right now, compatibility was my main goal in getting everything working. So I wanted to show you, that was add and everything we generate for add. But I wanted to show a couple of other examples of how we compile things. Loading constants is kind of interesting. If you ever looked at a code object, it has a co-const field on it, and things like none and one, like if you put one in a method, those are all going to be stored in this tuple that's hanging off of the code object. And the nice thing here is we can just burn the address of that object directly into the generated code. So it's just a x86 or x64 assembly instruction that's going to get generated that holds directly onto the address of that object, and we have to incref it because we have to ref count all over the place. Loading names, this is looking up a global, for example, or a non-local, potentially. Anything that isn't resolved into if you're inside of a class, variable lookups have to happen dynamically into a dictionary. And so in this case, again, we're just burning the address of the name object, which is a string object, and we're calling this one helper method to do the name lookup, and then if it fails, it will return null, and we have to check it, and all of that good stuff. Load attributes, similar to loading names, except for we have an object that we're loading it from. That was already pushed onto the stack, and we call the helper method, and you can see the pattern here. So a lot of this code generation is actually really simple and straightforward, which is kind of what I was expecting when I got started with the project. But there were challenges. And the first big one is really exception handling, which is a bit of a mess. And as I mentioned with the decref issue, still isn't quite entirely solved, but it's pretty close. Iteration was another one. There's a little bit of funkiness around there. And return and break and continue become kind of fun, especially in the face of exception handling. So with exception handling, we've seen all of the little error checks that are sprinkled throughout the code. Those aren't really too bad. They're just checking for null and then branching to a common label usually. And so they're not contributing a lot to code bloat. The real interesting thing about exception handling is that CPython actually has a second stack that it maintains that's there for both loops and exceptions. And so that's a big difference from .NET, where there's really just a single stack. The worst thing about that second stack is, well, there's two bad things. A, the stack depth ends up varying based upon the opcodes, which is something that .NET doesn't like. And the two stacks are a little intertwined. And you could actually construct bytecode by hand, which CPython will execute in a perfectly reasonable way that is going to interact with those two stacks in a very bizarre way. If you pay attention to what the CPython bytecode compiler is actually doing, it will never produce those bizarre sequences of opcodes. So we cheat, and you can actually compile a function by hand and pass in the bytecode by string and create a function that horrible things would happen to us with. And kind of the supreme example of this is the finally opcode, which behaves in a whole bunch of different ways. So this is what a simple try finally with no statements inside of it in CPython compiles into. It first does a setup finally, which pushes a block onto the block stack, pop block pops it off, and controls just flowing through here. So we completed the try successfully with no exceptions. So now we hit this load const, which is loading none. You don't see this none anywhere in your code, but it's there, and it's there so that finally can consume it and say, no exceptions happened, I'm just going to continue on to my next opcode, and we'll load const and return none as the default return value for a function. So finally popped one value from the stack. But finally can behave a little bit differently. So here we have finally inside of a loop, and we're breaking from the loop in the try block. So we have our setup loop, we have our setup finally, we have the break loop. Break loop is actually going to push an integer onto the Python stack. You don't see it. I don't remember what the number is. It's some bit flag. And we're going to pop the block, which pops the well, we're not going to hit the pop block because break loop is actually going to dispatch to the finally as it pops the block stack. So we go into finally with this value on the stack. Finally sees it, pops it, and knows that it needs to pop another block from the block stack. And then that happens, and it knows where to jump to. And so that's kind of another oddity. But finally can pop multiple values in the case of a return. And here, when we do the return, it's going to push us that same special integer that says what's going on, kind of like what break did, but it's a different integer value. And it's going to push the return value onto the stack. And then we're going to dispatch to finally, and it's going to pop two values off the stack. And then, yet another case is if we finally in an exception block. So what's really weird here is we have an finally opcode, but there's no setup finally. It just doesn't exist. We're ending a finally that was never there, and it just seems like someone had this complicated finally opcode that could easily be overridden. So what goes through is we are doing the match to see if we have an exception, and if we don't match the exception, then we'll pop forward to the finally, and the exception will be re-raised. So what's on the stack in this case is actually three values. You can see the three pop tops there. There's an exception value, an exception type, and a traceback. So I don't know how crazy that seems to you, but the big problem here is that the .NET IL definition is designed to be verifiable, and it's designed to know what's going on and be able to track values through the system and say, hey, you messed up a type here. CPython doesn't have those constraints, obviously. So with .NET, you cannot vary the stack depth based upon control flow, based upon values that are on the stack. And if you do, the JIT is going to blow up, and it's not going to know how to generate code. And so somehow, we actually have to make all of that work. And the way that works is, we can see these setup except, we can see these setup finally opcodes, and we can manifest that same block stack at compile time, just like CPython does at runtime, except for if there was crazy control flow, crazy weird bytecode not produced by the compiler, we're going to get very confused about how we manifest that block stack at compile time. Another fun thing is actually iteration. So in CPython, when you do for x in something, the first thing that happens is there's a get iter opcode which gets generated. And then the second thing that happens is there's a for iter opcode. And it's just going to loop around and call for iter on the iter value that came back from get iter over and over and over again. And it's going to leave that iterable value on the stack throughout the entire iteration. This is a little bit weird in that for iter will eventually pop that value off the stack and dispatch to the end of the loop. That's not particularly a huge problem. What's kind of confounding here is that .NET is very restrictive about leaving basic blocks with values on the stack in certain cases. And kind of the canonical one of those is returning with a value. So if you're iterating over something, you do return x and you have something on the stack, it is not happy. That might just be it being a little over restrictive, but that's kind of one of the limitations there. And so in a lot of cases, we have things like this jump absolute opcode. And for every opcode, we have a label that we define for IL. And if we need to jump to it, we jump to the spot where that label is. With for iter, we actually have to get that value off the stack. And so we store it into a local. And then that table needs to be slightly adjusted so that instead of branching to the instructions that we started emitting when we were encountering for iter, we're branching to a couple instructions later, which are actually just after we've loaded the iterable value out of a local. It's a little annoying and certainly not the worst thing in the world, but get iter and for iter aren't actually always paired. They can show up not being paired in the case of a list comprehension, so it gets a little bit complicated. The other fun thing is break, return, and continue, which all need to be aware of finally blocks, and we need to dispatch through them. So CPython ends up pushing these special values onto the stack, these integer values, and when it hits the in finally, it checks for those and then dispatches out to the block stack. And so when we hit a break, continue, or return, we actually have to go through the block stack and add dispatches out into the finallys. And we do the same trick, actually. Like our in finally blocks, we end up pushing special values on the block, and our finally blocks are always expecting to start with one value on the stack. And they'll check that value and then break, continue, or return. The nice thing is we can detect whether or not there's break, continues, or returns inside of these blocks, and we can get rid of those checks entirely if we don't need them. So that was just one more wrinkle in exception handling, and it took lots and lots of iterations of getting that all right, and just, it's like, oh yeah, got it right, nope, got it right, nope. So that was a lot of fun. So the real interesting question is, what does the perf look like? So I started this back at PyCon, actually, and I was able to get 2 numbers being added at PyCon, and I've been working through fleshing out support for all of the other bytecodes just about, and I've had no chance to really dig in and do any optimization work. My focus has been on completeness. So on this graph, numbers below the line are better, numbers above the line are worse, and numbers obviously on the line have no change. So there's a few things that got 15, 20% perf benefits. I left off startup on here because startup takes a big hit right now. These numbers are, we are JITting methods after they've been invoked 20 times, which is a rather low number. And so that probably impacts startup really horribly, but may make some of these numbers a little bit better for the perf runs, actually. So there's a lot of things that can still be done, and I'll talk about those in a second. But I think one important thing is, what is the overhead of actually JITting code? And that is, it's about 22 times slower to execute a empty method if we have to JIT it on its first invocation. And that is actually a really decent number. So I've looked at some LLVM implementations, and it ends up being over 1,000 times slower. This will probably get worse as more optimizations get added in, as we have to do some passes through the methods, but I don't expect it to get too much worse. And so I think that leaves a lot of hope for this implementation. So there are some things that we don't actually support yet. Yield and yield from are two kind of difficult ones. They shouldn't be too bad in that we just need to really set up the state machine and switch and branch to the opcodes after the yield opcode. The only difficult thing there is restoring values that were on the stack. So if you do a plus yield some value and have a someone sending a value back in, A needs to be stored on the stack and it needs to be restored when you come back in. So that will be a little bit difficult and will probably be the last thing to actually be supported. With statements aren't supported. Did I mention that exception handling was hard? So I don't think the with statement will actually be too much more difficult, but I'm sure there'll be some surprises there. And then, of course, the user-generated bytecode, which we have no way to detect, and will just kind of make us crash and burn in horrific ways. So I don't really know what to do about that. So there's a lot of low-hanging fruit that can be improved upon. So there's some things like you will compare two values and then do a value to check if they're the same, right? Or check if it's true. So A equals B, is this true? And in those cases, we can merge those opcodes into one piece of generated code, and we would avoid pushing a true onto the stack, bumping its ref count, popping a true off the stack, decking its ref count, and so on. So that is a pretty simple optimization which can be added in. We lost, CPython has an optimization which is there to reuse strings, like when you're doing a concat, and optimize the memory allocations there, and we lost that. I mentioned the checking to see if parameters were defined. Doing that with parameters will be really easy. Locals will be more difficult, but I'll probably do parameters pretty quickly. There's larger stuff. So type specialization, if we look at the values that are coming in, if they were ints, we could generate simple int addition, check for overflow, and return a new int rather than dealing with a bunch of Python objects. And as that expands, it becomes a more important optimization and doing inference to detect all of that stuff. Mono and polymorphic inline caches, that's something that we used a lot in IronPython, and so that is the ability to do some inlining of the code that you expect to be there, do a quick type check, and if the type's correct, then you can just go off and do whatever you need to do to make that happen instead of dispatching to a larger chunk of code. And so that will let things like inlining happen potentially, and for operations like addition, those could be inlined as well. Tagged pointers, this just lets you get rid of allocations for things like ints. And so rather than allocating a Py object, which is going to store a simple int, you can have an object where the lowest bit is set on it, because all objects have 0 bits set for their lowest bits, and you can have 31 bits of integer or 63 bits of integer stored there. And we can do this by passing our variables out by ref, and if we need to box them, we replace the tag pointer with a real pointer before we're calling into the Python runtime, and we don't allocate too many objects. Almost done. Iteration optimizations, range, avoiding allocating iterator objects for those. I think that's something I started looking at, but just haven't made much progress. Inlining, kind of combining with type specialization, moving things off of the frame object and into locals, and the loop compilation, which I have no clue how to do that with Python in the long term. But that's it. If there's any questions, I'll be happy to answer them. I posted the code at GitHub on my GitHub repo. I called it Pigeon. Just kind of, it's like unladen swallow, but it's a different bird. And it sounds like PyJIT, kind of. Brett?
So obviously the numbers, some of them look good, some of them don't. Do you have any feeling how much of the low-hanging fruit would have to get cleared out in order to make it pretty much across the board equivalent in terms of performance? And the other follow-up is like, is that partially just because you started with 20, after only 20 hits on a function, do you think changing that would help at all?
So I think changing the 20 hits will help on startup a huge amount. I think that number should be a lot bigger to help startup. It's kind of a ridiculously low number. I know Unladen Swallow was doing 10,000. I think there's, like some of the, going back to the performance benchmarks, some of the really bad ones were calls, which seemed really surprising to me. Those are the ones on the left, which are the worst here. And I think those will be some of the easiest things to actually optimize. There are actually a couple of benchmarks that are missing because I crash on them right now. I don't think it's that far off from getting to something that's like parity. Travis?
So GIL and the JIT.
This does nothing with the GIL. So kind of, I think one of the benefits of adding a JIT to CPython is that the rest of the world doesn't have to change, and that's a good thing in some ways. The GIL's going to be a different nightmare to get rid of, and this would play fine with the GIL or without the GIL. Ref counting obviously has to be solved for the GIL, and it will impact things either way, and whatever solution happens there, it should be easy to add it to the JIT. Shirok?
So just to clarify, so this JIT stack will be available on Linux and macOS as well, and in theory this will work on those platforms as well, yes, no?
Yes, in theory that will all happen. I don't know what the effort, where the efforts to port Core CLR to Mac OS X and Linux are right now. In fact, I snapped back to an old version of Core CLR, so it may be there. I just haven't gone back and checked, but they are absolutely porting to Linux and Mac OS X, and so we'll be able to benefit from that work. Yes?
So if I have some C#.NET code and I want to call some Python code, and I don't think I could use IronPython because it's like NumPy stuff.
Yep.
This will solve my problem?
Nope. So what you want is Python.NET. So Python.NET, make sure, I think you need to find the GitHub page. If you search for it, you're going to get some old page. But it's available. It's still being maintained. It has an interface that's very similar to IronPython, where you can do import CLR, CLR.add reference, and it's a bridge between Python and .NET. And so it's using the .NET hosting APIs.
At some point I found the old page for that and it was like, oh, it's not maintained.
Yeah, yeah.
If it is, that's
Find the new one. Someone picked it up.
Just a quick question. Can you comment a tiny bit on your compatibility with libraries like NumPy or compiled C extensions?
So compatibility should be perfect. Modulo, lots of bugs that I still have to work out. There's nothing in this which breaks compatibility in any way, shape, or form. We are right now it basically is unrolling the Python eval loop. And so it will be executing in the same basic manner, just faster, hopefully. Brett?
You want help with this?
Sure. There's instructions, a short README on how to set things up. It will download the dependencies. The source code on GitHub's just the JIT itself. It'll get Python and Core CLR and sync them back to the change that I tested and apply some small changes so that you get the JIT interface. And then you can build them, and those are woefully under-tested, so report any issues.
Quick question, not directly related to this talk, but Dropbox has another effort.
Yes, that's Piston,
Yes.
and it's a brand new Python implementation, which is a little bit crazy, but
So what's the difference for the uninitiated between what you're doing and a brand new Python?
so they have to go and recreate everything Python and get it perfect, the entire runtime. They want to put in a conservative GC. They went to, their JIT is based on LLVM, which is going to have the same slow startup costs that LLVM has. And it's just a huge amount of work for them to get from point A to point B to recreate all of the work that the Python devs have been working on for the past decades.
And this is,
This is CPython with a new DLL and maybe, I don't know, 30 lines of code changed in CPython to call into the generated code.
so you don't optimize all the code. The old CEval loop is still running it for some time.
Yes,
Some of the time.
yes. And in particular, like, there's no reason to JIT a module, right? Now, I started off JITting all of the modules just to kind of work through the code. There's almost no reasons to JIT a class definition. You could run a class definition in a loop and be dynamically generating classes, which are closed over things, and maybe that might matter at some point to someone, but it's pretty unlikely. And yeah, and then so we just JIT the methods that get invoked enough times, which is currently 20. All right, no more questions? Thank you very much.